Albert Einstein, the greatest physicist who ever lived. Relativity, E equals mc squared. The photoelectric effect, revolutionary insights that transformed our understanding of space, time, matter, and energy. A genius whose theories define modern physics. Except Einstein was wrong about quantum mechanics, about black holes, about the expanding universe, about cosmology, about almost everything that came after his greatest work. And when you understand how close Einstein came to being completely wrong about the universe, you will realize that even genius has profound limits. Albert Einstein is revered as the ultimate scientific genius. His name is synonymous with intelligence itself. When we want to call someone exceptionally smart, we say they are an Einstein. His image, that wild hair and penetrating gaze, adorns posters, T-shirts, and classrooms worldwide. His equations are carved into monuments. His ideas reshaped physics in ways no one before or since has matched. And yet Einstein spent the second half of his career being wrong. Spectacularly, stubbornly, fundamentally wrong about the most important developments in physics. He rejected quantum mechanics, the foundation of modern physics. He fought against black holes, which we now know fill the universe. He dismissed the expanding universe, the central fact of cosmology. He pursued unified field theories that led nowhere while the real revolutions happened around him. How did the greatest physicist of the 20th century end up on the wrong side of nearly every major debate? How did Einstein, who revolutionized physics with special relativity and general relativity, become the scientist who could not accept what those theories implied? The answer reveals something profound about science, about genius, and about the limits of human intuition, even at its highest levels. Let me show you where Einstein went wrong and why it matters. Einstein's greatest mistake began with quantum mechanics. In 1905, Einstein's miracle year, he published the photoelectric effect paper showing that light consists of discrete quanta, particles we now call photons. This was one of the founding papers of quantum mechanics. Einstein should have been the father of quantum theory alongside Max Planck. But as quantum mechanics developed in the 1920s, Einstein recoiled in horror. Werner Heisenberg discovered the uncertainty principle. You cannot simultaneously know a particle's position and momentum with arbitrary precision. The more precisely you measure one, the less precisely you can know the other. This is not a limitation of measurement tools. This is a fundamental feature of nature. Particles do not have definite values for both position and momentum simultaneously. Erwin Schrödinger developed the wave equation, describing quantum systems as wave functions, probability distributions rather than definite states. The wave function gives you probabilities for different measurement outcomes. Before measurement, the particle is in a superposition of multiple states. Measurement collapses the wave function to one definite outcome, chosen probabilistically. Einstein hated this. He famously said God does not play dice with the universe. He believed that quantum mechanics was incomplete, that underneath the probabilistic description, there must be hidden variables that determine outcomes deterministically. The apparent randomness is just ignorance of these hidden variables. Einstein spent years trying to prove quantum mechanics wrong. He devised thought experiments, paradoxes designed to show that the theory leads to contradictions or absurdities. At the 1927 Solvay conference, Einstein challenged Niels Bohr with a series of ingenious arguments against the uncertainty principle. Bohr refuted each one. Einstein kept trying. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published the EPR paper arguing that quantum mechanics must be incomplete. They described a thought experiment with entangled particles. Measure one particle, and you instantly know the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance and argued it was absurd. Either information travels faster than light, violating relativity, or the particles had definite states all along that quantum mechanics just does not describe. Einstein was certain this proved quantum mechanics was wrong or incomplete. He was wrong. John Bell developed a mathematical test in 1964. If hidden variables exist, certain statistical correlations must obey Bell inequalities. If quantum mechanics is correct, those inequalities can be violated. Experiments were performed. Bell inequalities are violated. Hidden variables do not exist. Quantum mechanics is correct. Reality at the fundamental level is genuinely probabilistic and non-local in ways Einstein found intolerable. Einstein never accepted this. He died in 1955 still believing quantum mechanics was wrong, still searching for a deeper deterministic theory underneath. He was wrong. Quantum mechanics is one of the most successful theories in physics. Every prediction it makes has been verified to extraordinary precision. The probabilistic nature Einstein rejected is fundamental to reality. His intuition, usually so reliable, failed him completely. The second major area where Einstein was wrong concerns black holes. In 1915, Einstein published General Relativity, his masterpiece theory of gravity and space-time. Within months, Carl Schwarzschild found an exact solution to Einstein's equations, describing what happens around a massive spherical object. This solution predicted something strange. At a certain radius, the Schwarzschild radius, space-time becomes so curved that nothing can escape, not even light. This is a black hole. Einstein rejected this solution. He thought the mathematics was correct but physically meaningless. Real objects could never compress to the Schwarzschild radius. Some physical process would prevent collapse. Black holes were mathematical artifacts, not real objects that could exist in nature. For decades, most physicists agreed with Einstein. Black holes seemed too bizarre to be real. But in the 1960s, Roger Penrose and Stephen Hawking proved theorems showing that black hole formation is inevitable. When a sufficiently massive star runs out of fuel and collapses, nothing can stop it from forming a black hole. The singularity at the center is unavoidable. Black holes must exist if general relativity is correct. Observations confirmed this. We found stellar mass black holes in binary star systems, accreting matter and emitting X-rays. We found supermassive black holes at the centers of galaxies, including our own Milky Way. We detected gravitational waves from black hole mergers. The Event Horizon Telescope imaged the shadow of the supermassive black hole in galaxy M87. Black holes are real. They are common. They fill the universe. Einstein never accepted black holes as real objects. He published a paper in 1939 trying to prove they could not form. He was wrong. Black holes are some of the most important objects in the universe, crucial to understanding galaxy formation, gravitational waves, and the nature of space-time. Einstein's theory predicted them, but Einstein himself refused to believe they existed. The third major area where Einstein was wrong is cosmology and the expanding universe. In 1917, Einstein applied general relativity to the universe as a whole. The equations predicted the universe should be either expanding or contracting. But Einstein, like everyone at the time, believed the universe was static and eternal. To make his equations compatible with a static universe, he added a term, the cosmological constant, a form of energy density that could exactly balance gravity and keep the universe from expanding or collapsing. Then in 1929, Edwin Hubble discovered that distant galaxies are receding from us. The further away a galaxy is, the faster it recedes. This is exactly what general relativity predicts if the universe is expanding. The cosmological constant was unnecessary. Einstein later called it his biggest blunder. He should have trusted his equations and predicted the expanding universe before it was observed. But Einstein's mistake went deeper than just adding the cosmological constant. When the evidence for expansion became overwhelming, Einstein resisted. He questioned Hubble's observations. He proposed alternative explanations. He struggled to accept that the universe had a beginning, that all of space and time emerged from an initial state billions of years ago. The concept of the Big Bang seemed absurd to him. Georges Lemaitre, a Belgian priest and physicist, proposed that the universe began from a primeval atom, a hot, dense state that expanded and cooled. Einstein dismissed this as mixing physics with religion. When Lemaitre presented his ideas at a conference, Einstein stood up and said, "Your calculations are correct, but your physical insight is abominable." Einstein was wrong. The Big Bang model became the foundation of modern cosmology, confirmed by the cosmic microwave background radiation, the abundance of light elements, and the large-scale structure of the universe. The irony is devastating. Einstein's general relativity predicts the expanding universe, black holes, and the Big Bang. But Einstein himself rejected all three. His equations were smarter than he was. The mathematics contained truths Einstein could not accept. The fourth area where Einstein went wrong is his pursuit of a unified field theory. Einstein spent the last 30 years of his life trying to unify gravity and electromagnetism into a single geometric framework. He believed that a truly fundamental theory should describe all forces geometrically as manifestations of space-time structure. This quest led nowhere. Einstein produced dozens of papers proposing different unified field theories. None worked. None made testable predictions. None explained the nuclear forces that were being discovered. Einstein was pursuing a dead end, trying to unify two forces while ignoring the other forces and failing to account for quantum mechanics. Meanwhile, physics was undergoing revolutions Einstein ignored. Quantum mechanics was being extended to quantum field theory, describing particles as excitations in quantum fields. The weak and strong nuclear forces were discovered and incorporated into the Standard Model. Physicists realized that unifying forces requires quantum field theory, not classical geometric theories like Einstein was pursuing. Einstein rejected quantum field theory. He rejected the idea that particles are fundamental. He rejected the entire direction physics was taking. He worked in isolation, stubbornly pursuing classical unified theories while the rest of physics moved on. By the 1940s and 1950s, Einstein was no longer at the forefront. He was a relic, respected for past achievements, but ignored because his current work was irrelevant. The tragedy is that a true unification does seem possible, but not the way Einstein envisioned. The electroweak theory unified electromagnetism and the weak nuclear force. Grand unified theories attempt to include the strong force. String theory offers a framework for including gravity, but all of these require quantum mechanics. Einstein's refusal to accept quantum mechanics meant he was chasing a theory that could never work. The fifth area where Einstein was wrong concerns the nature of time. In special relativity, Einstein showed that time is relative. Different observers moving at different velocities experience time at different rates. There is no universal now. Simultaneity is relative. This was revolutionary. But Einstein interpreted this to mean that time is not fundamental, that the flow of time is an illusion. In general relativity, space-time is a four-dimensional structure where all events exist eternally. Past, present, and future are equally real. The block universe. Einstein embraced this view. He wrote to the family of his deceased friend Michel Besso saying that for physicists, the distinction between past, present, and future is a stubbornly persistent illusion. This view is deeply problematic. It cannot explain the arrow of time, why entropy increases, why we remember the past but not the future, why cause precedes effect. Einstein never solved these problems. He dismissed them as psychological rather than physical, but they are physical. The second law of thermodynamics is one of the most fundamental laws in physics. Time's arrow is objective and observable. Modern physics recognizes that time is fundamental, not illusory. Quantum mechanics requires time evolution. Thermodynamics requires temporal direction. Cosmology requires cosmic time. Einstein's view that time is illusory was another case of his intuition leading him astray. The sixth area involves statistical mechanics and Boltzmann's work. Einstein made important contributions to statistical mechanics, confirming the atomic theory of matter and explaining Brownian motion. But Einstein never fully appreciated Ludwig Boltzmann's deeper insights about entropy and the arrow of time. Boltzmann showed that the second law of thermodynamics is statistical. Entropy increases because high entropy states are vastly more numerous than low entropy states. Einstein acknowledged Boltzmann's work, but did not incorporate its implications into his thinking about cosmology and time. If Einstein had fully embraced Boltzmann's ideas, he might have understood why the universe needs a low entropy initial state and how this gives time its direction. Instead, Einstein remained puzzled by time asymmetry and never developed a satisfactory explanation. Now, it is important to be fair. Einstein was not wrong about everything after general relativity. He made important contributions to quantum theory, even as he rejected its implications. He understood gravitational waves, though he flip-flopped on whether they were real. He proposed the Einstein-Podolsky-Rosen paradox, which led to Bell's theorem and deeper understanding of quantum entanglement. Even Einstein's mistakes were often fruitful, stimulating research that ultimately proved him wrong but advanced physics. And we must acknowledge the extraordinary difficulty of what Einstein achieved. Special relativity and general relativity are among the greatest intellectual achievements in human history. They required overturning centuries of intuition about space and time. They required mathematical sophistication and physical insight of the highest order. Einstein did this largely alone, without the institutional support and collaboration that drive modern physics. But the fact remains, Einstein was wrong about quantum mechanics, the foundation of modern physics, wrong about black holes, which are now central to astrophysics, wrong about the expanding universe and cosmology, wrong in his pursuit of classical unified field theories, wrong about the nature of time, wrong about so much that came after his greatest work. Why? How did this happen? Part of the answer is age. Einstein was 26 when he published Special Relativity, 36 when he completed General Relativity. Revolutionary physics tends to be done by the young. By his 40s and 50s, Einstein's thinking had calcified. The intuitions that served him so well in developing relativity became obstacles when confronting quantum mechanics. Part of the answer is philosophy. Einstein was deeply influenced by Ernst Mach's empiricism and Baruch Spinoza's determinism. He believed the universe must be deterministic, that everything must have a cause, that God does not play dice. These philosophical commitments blinded him to the evidence that nature is fundamentally probabilistic. Part of the answer is stubbornness. Einstein invested decades in his opposition to quantum mechanics and his pursuit of unified field theory. Admitting he was wrong would have required abandoning work that defined his later career. The sunk cost fallacy applies even to genius. Part of the answer is isolation. Einstein spent his later years at the Institute for Advanced Study in Princeton, somewhat removed from the mainstream of physics. He did not engage with the quantum field theorists and particle physicists who were building the Standard Model. He worked with a few collaborators on his unified field theories, but they were pursuing a dead end together. But the deepest answer is about the limits of intuition. Einstein's intuition was extraordinary. It allowed him to see that time is relative, that space curves, that mass and energy are equivalent. But intuition, even Einstein's, has limits. Quantum mechanics is deeply counterintuitive. Particles in superposition, wave function collapse, entanglement, these violate all classical intuitions about how reality should work. Einstein could not force his intuition to accept quantum mechanics, so he rejected it instead. This reveals something profound about science. Science is not about genius. Science is about method. You make hypotheses, you test them, you follow the evidence wherever it leads. Einstein followed the evidence in developing relativity. But when the evidence pointed toward quantum mechanics, toward black holes, toward the expanding universe, Einstein resisted. He trusted his intuition over the evidence, and his intuition was wrong. The younger generation did not have Einstein's intuitions to overcome. Heisenberg, Schrödinger, Dirac, they came to physics after relativity was established. They did not need to develop the revolutionary insights Einstein had. They just needed to follow the mathematics and the experiments. And they did. They built quantum mechanics into the most successful theory in physics, while Einstein stood aside insisting it must be wrong. The lesson is that even the greatest minds can be wrong. Even revolutionary insights have limits. Even genius must bow to evidence. Einstein transformed physics twice, but he could not transform it a third time. The universe proved stranger than even Einstein could accept. And that is actually inspiring. It means science works. It means theories are tested against reality, not against authority. It means Einstein's objections to quantum mechanics were considered seriously, tested experimentally, and found wanting. Science does not care about reputation or past achievements. Science cares about what is true. Einstein was almost completely wrong about physics after general relativity. But physics moved forward anyway. Quantum mechanics, black holes, the expanding universe, the Standard Model, all developed despite Einstein's opposition. Truth won, and that is how science is supposed to work. Einstein remains one of the greatest physicists who ever lived. Special and general relativity are towering achievements, but Einstein's later failures are just as important as his earlier successes. They show that science is bigger than any individual. That evidence trumps intuition, that being wrong is acceptable, even necessary for progress. Einstein was wrong, and physics is better for having proven him so. Consider what modern physics would look like if Einstein had been right. If quantum mechanics were incomplete and hidden variables existed, quantum computing would be impossible. Quantum entanglement would not work as we observe. The precision of atomic clocks would be unexplainable. Chemistry would not function as it does. The Standard Model would collapse. If black holes did not exist, we would not observe X-ray binaries, quasars, or gravitational waves as we do. Galaxy formation would be unexplained. The observations of the Event Horizon Telescope would be impossible to interpret. Einstein's own equations would predict phenomena contradicted by reality. If the universe were static and eternal, as Einstein initially believed, the cosmic microwave background would not exist. The abundance of hydrogen and helium would be wrong. Distant galaxies would not be receding. Everything we observe about cosmology would be inexplicable. Einstein was wrong, and the evidence overwhelmed his objections. This is how science should work. Even Einstein, even genius itself, must yield to observation and experiment. That is not a failure of Einstein. That is the success of science. We honor Einstein not just for being right about relativity, but for being wrong about quantum mechanics in ways that forced the theory to be rigorously tested and confirmed. His opposition made quantum mechanics stronger. His skepticism required proofs that might otherwise have been postponed. Einstein's wrongness served science even as it frustrated him. The next time you hear Einstein's name invoked as ultimate authority, remember that Einstein was magnificently wrong about most of 20th century physics. Genius has limits. Intuition fails. Only evidence and rigorous testing reveal truth. And that is the real lesson Einstein's life teaches us.